Hello and welcome to Calculus section 6.3, multiplying a vector by a scalar. So in the previous sections we saw what a vector is. So a vector is a quantity that has both magnitude and direction. So we represent it with an arrow. The length of the arrow denotes the magnitude, and the direction, well, that tells you which way it's going. So I've got vector u here. I denote that it's a vector by putting a little arrow on top. Okay, so now if I want to take that vector u and I want to make it 2 times as long, I would write that as 2u. Okay, so that would mean that the magnitude is twice as big, but it's going in the same direction. So I'm going to take my ruler and make sure that it's about parallel here. So actually, if I want to keep this really accurate, this right now is about 3 centimeters. Okay, so I'm going to go ahead and make 2u 6 centimeters, but in the same direction. Okay, so that would be 2u. That is a scalar multiple, right? So same direction, it might be in a different spot, but same direction, different magnitude. Now, I don't just have to multiply by a positive number. I can even multiply by a negative number. I can even have something like negative 1.5u. Okay, so first things first, look at the positive 1.5 part of it first, the magnitude. 1.5u means it's 1.5 times as long as u, so 50% longer than this. Okay, so if this is 3 centimeters, half of 3 is 1.5, making the length of this 4.5 centimeters. So I'm just going to draw something that's 4.5 centimeters. Don't draw the arrow yet. So 4.5. Now the fact that there's a minus sign tells me it's going in the opposite direction. So it's not going up and to the right, it's going down and to the left. Okay, so that's what minus 1.5u looks like. So in reality, you can put any number in front that you want. So it doesn't have to be 2 or negative 1.5. It can be pi. It can be negative 1,637,000. Although we're not going to go that extreme. The idea is that in order to have a scalar multiple of a vector u, this is just going to be a constant k times the vector u, where k is an element of the real numbers, which means k can be positive, it can be negative, it can be a decimal, it can be an integer, whatever you want. Okay, so what that tells us is that there's a couple of things. First of all, you can obtain opposite vectors. You can even obtain an equivalent vector, right, by making k equal to 1. Okay, notice that all of these vectors are parallel. Okay, so all of these vectors will be parallel. There's going to be another way we can denote these, which we'll see later on in the lesson. So let's move on to the first example. Okay, example 1. I'm going to draw some vectors here, and I want you to copy them down as closely as you can. So I've got here vector f, I've got vector c, I've got vector d. Now, if you don't want to copy this down, actually, maybe it's best to just look at it, because maybe you're not going to know exactly how to copy it down. That's V, that's A, that's H, that's B, we've got E, and let's get one more here, G. Okay. So you've got a series of vectors here, and the question is, which are scalar multiples of V? So these questions you're going to find, well, these examples are going to be mirroring the ones in the book. They're a little different at the same time, so if you need more practice with this, you can always consult the pages in the book and get more practice. But I mean, for now, we're looking at this. Okay, so we're looking at which are scalar multiples of vector v. Now, you know, in order for it to be a scalar multiple of vector v, it's got to be parallel. Now, it doesn't have to go in the same direction, but it's either the same or the opposite direction. And what I find is that the only vectors parallel to v are c, b, and g. Those 3 are parallel. Okay, so I've got 2 of those vectors, c and g, that are going in an opposite direction. So these 2 would have k values that would be negative, Okay, and B here would have a K value that's positive, but it's going to be less than 1. Okay, because you see that it's shrunk compared to V. So which ones are scalar multiples of V? The answers are C, B, and G. Okay, so hopefully that's okay. If you're wondering why the other ones are not scalar multiples, so for example, F, there's no constant that you could possibly multiply to V to get F. F is going in a completely different direction. All right, so if I multiply V by any number, whether it's 5 or -3 or 0.7, it's just going to change the length or make the direction opposite. You will never make it anything but parallel to what its direction is right now. Okay. Let's move on to another example. Okay, actually, let's start at the bottom of this page. No, let's move on to a fresh page, actually. Example 2. Okay. So again, mirroring the examples in the book, but a little bit different at the same time. Okay, so we've got a vector W whose magnitude is 500 kilometers per hour. So maybe this is a plane flying in the air, some kind of an Airbus. Okay, so, and this is moving at a true bearing of 160 degrees. So let's refresh our memory. True bearing means you measure this angle from the north and clockwise from the north. And whatever angle you have, it has to be 3 digits. So if this was 45 degrees, you would express it as 045 degrees. Oh, so let me actually just move this here. There we go. Okay, so I'm going to go ahead and sketch this first, and then we will go ahead and address the problem. So I've got my Cartesian coordinate system. I'm going to just sketch that in. So there's y, there's x. Okay, so let's see, I've got 500 kilometers per hour at 160 degrees. So 0 degrees is up here on the positive y-axis. 90 degrees would be here. So this would be east. Right? So we've got north up here. We've got east. Down here would be south. This is 180 degrees. So 160 is about in this quadrant right here. So something like that. So we've got 160 degrees. Okay. So this is what we're dealing with right now. Now let's look at what we need to answer. Part A, we need to sketch the vector 2u. We're going to sketch the vector for part B, -u, and for part C, we're going to sketch the vector 0.5u. Okay, so actually keeping that in mind, I'm going to actually draw this a little bit shorter, otherwise it's going to be a little tricky to fit 2u in this picture. So give me 1 second, let me grab my whiteout. Because otherwise it's going to be tricky to fit all of this in. So I'm going to just make that a bit shorter. Okay, no harm done. There we go. Okay, so that's my 500 kilometers an hour. That's W. So we should actually turn this into a W, this into a W, and this into a W. Okay, good. So drawing in our vectors, let's start with 2W first. So this is a vector that has the same direction as W, but, well, twice as long. All right, so we're going to grab our ruler. This vector right now is it's almost 3 centimeters. So we'll make this 6 centimeters. Okay, so same direction. We're just going to extend it. Okay, so of course this vector is starting from the origin. So if you want, you can actually draw it in there as well. But there it is. There's 2W. And I'll just go ahead and label this one here U. Okay. Same direction, twice as long. All right, -W. Okay, magnitude is the same, but it's going in the opposite direction. Okay, so magnitude is 3. To see the opposite direction, well, just keep your ruler here. Okay, so I need 3 centimeters in the opposite direction, so I'm going to position my ruler as so. And there we go. So there is your -W. Keep writing U, -W. And finally, 0.5u, it's in the same direction as w. I keep saying u for some reason. Okay, this is a w, 0.5w. In the same direction as w, but half as long. So if this is 3 centimeters, it's going to be 1.5. So here we go, 1.5. This one's a bit harder to draw. Let me just make it a bit thicker here so you see it. Okay, so that's 0.5 w. And I gotta make that a W as well. Okay, U's, W's, whatever. They're letters. So, all right, opposite vector, half as long, twice as long. Okay, I hope that's okay, aside from the confusion of the letters. Now, with regard to the direction, okay, so for example, originally W was at a true bearing of 160 degrees. Okay, so 2W would also be at a true bearing of 160 degrees. 0.5W would also be at a true bearing of 160 degrees. Now, minus W, let's see that. If this whole thing is 160 degrees, this angle in here, well, that's going to be 180 minus 160. That's 20 degrees. And if that's 20 degrees, this is 20 degrees. Right? This angle up here is 20 degrees as well, which means the angle to get from north going clockwise to get to that terminal arm, that's 360 minus 20. So the angle to get here, okay, so that's going to be 340 degrees. So minus W is at a true bearing of 340 degrees. Okay, hopefully that's okay. Now we're going to move into a little bit of a definition here. And that definition has to do with vectors being collinear. Okay, so in past math courses, you may have been exposed to the term collinear. And usually that was with respect to points. So if I have, for example, an XY coordinate system and I have a straight line and I have, let's say, 3 points on it, A, B, and C. A, B, and C are collinear because they exist on the same line. But point D is not collinear with A, B, and C since it is not along a straight line connecting those points. Okay, so that's how it was in the past. Now we're looking at collinear vectors. So it's a similar idea. If I have vectors that I can line up such that they are arranged in a straight line, well, that makes them collinear vectors. Okay, so let's say I've got something like this, U, V, let's make that W. Okay, I've got 3 vectors, U, V, and W. When I arrange these vectors tip to tail, okay, almost as if I was trying to add them, the only vectors that would line up would be U and V. Okay, so U connected with V, these would line up and create a straight line. So U and V are collinear vectors. But if you try to connect W with U or W with V, so I would have U and I would have W, that's not a straight line. And if I try to connect V with W, also not a straight line, right? So you are not connecting them such that they are parallel. So what that shows us is that in order for vectors to be collinear, they need to be parallel. So these are not collinear. Okay, so a couple things. In order for 2 or more vectors to be collinear, well, they have to satisfy some requirements. Well, we already determined they have to be parallel. But from the first page that we were looking at, when vectors are parallel, that also implies that they are scalar multiples of each other. So these are really just 2 ways of saying the same thing. Okay, so a third way of saying the same thing, the 2 vectors are parallel, they're scalar multiples, we say that they are collinear. So in fact, we don't actually need a third point here. The third point would just be parallel and scalar multiple is the same thing as saying they're collinear. Okay, so all those expressions are equivalent. All right. we're going to look at, well, what happens if you multiply a vector sum by a scalar quantity? How do we deal with that? So let's say I have two vectors, u and v. So clearly these are not the same u and v that we just saw in the previous case. Okay, we have two vectors, u and v, and I want to add them. Okay, so if I add them tip to tail. So I attach the tail of v onto the tip of u. Okay, and my resultant, the total, is from the tail of the first vector to the tip of the final vector. So this is my sum. It's the resultant. That's u plus v. Now, I can say that u plus v is equal to u plus v. Okay, so what's the point of that? Well, I know that if I have scalars, so if I have just numbers on the left and right and I multiply one side by a constant, I have to multiply the other side by the same constant. What I do to the left, I have to do to the right. So, I mean, let's say I multiply the right side by k. I would get k u plus v. Okay, and on the left side, well, I would hope that I would get k u plus v, right? Which then I would anticipate to be able to distribute the k into the u and the v, resulting in ku plus kv. So the idea here being that ku plus v is equal to ku plus kv. Okay, so what that means is if I multiply each of the individual vectors by the same scalar multiple, that's the same as multiplying their sum by the same scalar multiple. And this is in fact the case. So if I make, well, u k times as long, so if I have k times u, and then I have k times v, their sum is also going to be k times as long. So this will be k times u plus v. So this is called the distributive property of vectors. And just as we can distribute a constant, so let's say 3 into the expression x plus 1, and we know that it's equal to 3x plus 3, we can also have the distributive property applied to vectors. So if I have 2 times a vector x plus vector y, this is equal to 2x plus 2y. Right? That's all it's saying. Okay. The last example that I'm going to do is actually exactly the example in the book. So what I want to do here is actually just, give me one moment actually. Okay, so I'm going to put the book up on the screen just for a moment so you see which page and which question we're going to be doing. Okay, so we're going to do example 3 on page 333. Okay, so example 3 here it is in trapezoid ABCD. BC is parallel to AD. AD is equal to 3BC. We're going to let the vector AB be called U, and BC is going to be called V. Express AD, BD, and CD as linear combinations of U and V. Okay, so linear combination. Okay, so this is what it means to have a linear combination. I'll show you. And this is essentially what the example is meant to demonstrate. So what I'll ask is if you can write down these main pieces of information on your sheet and sketch this picture on your sheet as well. Okay, so I'm going to do the same thing here on my side. I'm just going to sketch them in. Okay, so if you want to pause the video at this point, you can to copy it down. Otherwise, I'm going to go back to my paper here. Okay. So here we go. So I've got a trapezoid. I'm going to sketch it here. So I've got, let's see, this is one side, then I've got a short side, longer side, and then this is the joining piece. Okay. So 2 of these sides are actually labeled formally with vectors. Okay, so this side is U, this side is V, and the corners are A, B, C, and D. Okay, now what am I given? It's a trapezoid. I know that BC is parallel to AD. Okay, so that means that these 2 lines are parallel to each other. I know that AD is equal to 3BC. So this line is 3 times as long as this line. Okay. Let's see, and we know that AB is represented with U, just to keep it short and sweet. And BC is represented with V. Okay. Express AD, BD, and CD as linear combinations of U and V. So what that means is when I try to come up with an expression for AD, BD, CD, I can only give the answer in terms of U and V. So I might have 2U plus 3V is equal to AD. Okay, that might be the case, and that is a linear combination. So I can take a scalar multiple of one vector, whether positive or negative, and add or subtract a scalar multiple of another vector in order to obtain my desired vector. Okay, so I have to get AD, BD, and CD. So I'm going to start off with AD. So AD is the vector starting at A and culminating at D. Okay, so I have to go from here all the way here. So how do I do that? Well, I already know a vector that's in the same direction as AD. Okay, that's this one right here from B to C, and that's called V. Since this line BC is parallel to this line AD, that tells me that a vector going from A to D is going in the same direction as a vector that goes from B to C. Okay, and the vector that goes from B to C is V. And since this is 3 times as long, therefore I need 3 V's to go from A to D. Okay, so this is 3V since AD is parallel to BC. Yes, it's true that the line segments are parallel, but so are the vectors. They're also parallel, and they're scalar multiples of each other. Okay, and due to this reason and this reason, we can state that this is correct. Okay, so there's AD. The other ones won't be quite that fast, but nonetheless, they're not going to be difficult. Okay, BD. Okay, so the vector BD, I just want to sketch this in because this one's a bit harder to see. Okay, BD is the vector that starts at B and culminates at D. So it looks like this. Okay, so there's BD. Just, I guess, for completeness sake, AD was right here. Okay, so BD. Well, there's no vector that goes directly from B to D, unfortunately. What I could do, and what most people see first, is say, well, I could go from B to C and then add C to D. And that would work, except I don't have a vector representing CD. So I have this vector, which I can call V, but I don't have anything here. Okay, that's a bit of a problem. So if I can't go this way, towards the right or clockwise, I go towards the left or counterclockwise. Okay, so I now know that, well, this side is represented with U, the vector going from A to B, and I know the vector from A to D. I just found out that this is 3V. Okay, so that's going to help me. In order to go from B to D, I'm going to have to go from B to A first, and then afterward from A to D. Okay, so BD is going to be BA plus AD. Now, AD, I just found it's 3V, so I'm going to replace that with 3V. Now, BA, be careful. Okay, BA is not equal to U. U is AB. Okay, so if you remember from the previous lesson, AB and BA are opposite vectors. So AB is equal to negative BA. Okay, so AB is what's equal to U. So U is equal to, well, negative BA. And negative BA is equal to AB. So therefore, BA is equal to negative U. Okay, so if that's a little bit too complicated to follow, just look at the picture. The vector U goes from A to B, so therefore the vector going from B to A has to be negative U. Same magnitude, opposite direction. Okay, so I stick a little minus U in there and then plus 3V, and I'm done. So that's BD. Okay, last but not least, CD. All right, so for CD, let me grab another color here. For CD, I'm going from point C to D, and unfortunately, for the exact same reason that I just expressed, there is no vector. Oh, this pen is unfortunately dead. Let me pick a different color. There we go. Unfortunately, there's no vector going directly from C to D. Okay, so I have to go in the other direction. So to go from C to D, first I'm going to go from C to B, and then from B to A, and then from A to D. Okay, so I'm going to go C to B, and then B to A, and then A to D. Still going to get to my destination, tip to tail, and my resultant will be CD, just maybe not quite as fast. That's okay. So CD is equal to CB, right, plus BA plus AD, right? Now, looking at this, I already know what the BA plus AD is equal to. It's right here. I already know it's minus U plus 3V. So I just have to figure out what CB is. Now, CB is going in the opposite direction of BC. BC is V. Okay. So therefore, CB would be negative V. So this is negative V. And this piece here, BA plus AD, well, that's right here, which we found out was negative U plus 3V. So minus U plus 3V. Everything is addition here, so I'm not putting the brackets. Otherwise, you need to be careful with the brackets. And finally, collect your like terms. I have two sets of V's, so 3V minus 1V. That's 2V. So 2V minus U is equal to CD. And that is the answer for that last piece there. Okay, so what I can see is that when you have a linear combination, I mean, that's what you have here. If you have more than one vector being added or subtracted together, you have a combination of vectors. And when you have a linear combination of vectors, well, that just means that you start multiplying each vector by a constant that's not necessarily 1. So for example here, BD is made from a linear combination of U and V. Right? You don't have U, you have negative U. And you don't have V, you have 3V. Okay, for CD, I don't have V, I have 2V. And here I have minus U. Okay, so if we go back to the textbook here for a moment, just to take a look at the definition for linear combinations. Given two vectors u and v and scalars s and t, which are elements of the real numbers, then su plus tv is a linear combination of u and v. And that's exactly what we have in this example. Okay, our scalar multiple for BD is going to be -1 and 3 for u and v respectively. And for CD, the scalar multiples are 2 and -1. That's all it means to have a linear combination. So that is the end of lesson 6.3, a scalar multiples of vectors, multiplying a vector by a scalar. Stay tuned for future videos. That is going to be the end of chapter 6 lessons. Okay, so we're not going to be doing 6.4 and 6.5, but next chapter we will be moving into 7.1, 2, 3, 4, and 5. Okay, so stay tuned for those videos.